So I'll write down the rules for GN. So draw all possible topologically inequivalent diagrams with n external points. So all possible topologically equivalent diagrams within external points x1 to xn, and then for a propagator, for each propagator you write 1 over I delta x minus y. And multiply by symmetry factor 1 over s. This is equal to 1 always. We just saw that in free theory. Okay, but in the interacting theory, there can be a mismatch in the cancellation. So cancellation may not be complete, and one might be left with some additional symmetry factor at the Green's function level as well. Now, I wanted to say something here. Anyway, so I think that's I don't remember. So now let me move on to the interacting theory. So let me recall that defining equations. So recall the Green's function is given by the vacuum expectation value of time ordered product of in phi hats, and that has the path integral expression d phi e to the I by h bar s phi x1 to phi xn divided by d phi e to the I by h bar s phi, and that's the definition of the Green's function. And then Wj is in the path integral language, it's given by I by h bar s phi comma j divided by integral d phi e to the power I by h bar s phi, where s phi comma j is the free theory Lagrangian, integral of the free theory Lagrangian, then the potential minus v phi, then this source term. Okay, and this v phi is given by lambda 3 by factorial 3 phi cube plus lambda 4 by factorial 4 phi to the power 4, and so on. Okay, this is the free Klein-Gordon Lagrangian density. Now, in the free case, what we had done is that integrated phi completely and gotten an expression, explicit expression in terms of J. Question, so we have to do the same thing here, but because of this potential, there is a problem here. The potential, when it appears upstairs, that can still be managed, but it is difficult to manage when the potential is downstairs. So the question is that how would you, so there is the direct method. So there is no direct method, but we would adopt an indirect method. In the free theory, the full path in the phi integration could be done because the path integral, because it was quadratic in phi, and now it is not, and therefore this integral cannot be done. But what is the best way to handle this? So we shall develop certain tools to describe Wj completely in terms of Feynman diagrams. And there are two steps in this. There are two basic points. One is that this V phi can be replaced by a certain number of derivatives with respect to J, acting on the original path integral without V phi. That is one. That is how you handle V phi upstairs. And when V phi appears downstairs, the way to handle it is that actually you calculate S0 by, in the downstairs you write S0 and then separately calculate the ratio of the path integral with S divided by S0. So that way you have to do two calculations and analyze this. But the analysis is nice and quite illuminating, and we shall now execute that. So it is because of that these two subtleties, that two methods that we are using to calculate it, that we define an alternative quantity called W tilde to facilitate this procedure. So don't get surprised by why I'm defining W tilde. Basically, as we shall see at the end of the discussion, towards the end of the discussion, that the motivation for defining W tilde is to actually enable us to do whatever I just described a second ago. So define W tilde of J, which is given by integral d phi e to the power I by h bar s phi comma j divided by integral d phi e to the power I by h bar s 0 phi. Actually, Wj will have s phi downstairs, but we are taking the free Klein-Gordon here to facilitate our calculations. But ultimately, we will calculate Wj, as I said. So this implies that the W tilde 0 is given by integral d phi e to the power I by h bar s phi divided by integral d phi e to the power I by h bar s 0 phi. And therefore, W tilde j is nothing but W tilde 0 times W of j. W of j has this divided by path integral with s, not s0. So that is, so this is we have s downstairs in Wj, but W0 has s upstairs and s0 downstairs, right? And that is why you are getting this divided by s0, and that is W tilde, right? So basically wj is equal to w tilde divided by w tilde 0, which is why you are dividing, you are taking this and divide by this quantity, then s0 path integral will cancel. You will have this in the downstairs, which is wj. But if you now set j equal to 0 on both sides, then that would imply that w of 0, this is w tilde 0, this is also w tilde 0. So w of 0, which is the vacuum overlap, the interacting theory vacuum, that is 1. Okay. Now I will describe a perturbative evolution of w tilde j, and that will tell us, that will take us eventually to the calculational tools for wj. So perturbative evaluation of w tilde j. So apply that trick that I said earlier for w tilde j. So let me write d phi e to the power. I'm separating out the potential piece from the interacting theory action, and then write e to the power I by h bar is 0 phi comma j divided by integral d phi e to the power I by h bar is 0 phi. Now use the fact, so we derived it earlier, that if you take a derivative del I jx of e to the power I times j phi, then it is an integral, and that integral, suppose it is integration over y, then it will be the same exponential j phi, but then del j of this I cancels, and then del j of this can be calculated by demanding that del j x is Kronecker Dirac delta y minus x, and that integration will produce phi x. So it will give you a phi x factor in front. So if you see a phi x factor in front, then that can be replaced by a derivative with respect to j, right? So you can use this to write you do such trick all the time in Fourier transformations, and so you can use this to write any path integral where phi, if functional of phi appears I by h bar is 0 phi plus I j phi is equal to f of phi replaced by del over I del j, acting on d phi e to the power I by h bar is 0 phi plus I j phi. Right? Or maybe I can just simply write it as S0 j phi. Phi comma j. Yeah. So we have the same form here. If a phi is nothing but this exponential minus I by h bar v phi, integral of v phi. So I can use this result and write this exponential minus I by h bar v of phi and replace phi by this derivative and take this out of the path integral, and then I have a path integral d phi e to the power I by h bar is 0 divided by d phi is 0 phi comma j divided by d phi e to the power I by h bar is 0. So that is w0, that ratio is w0. So This will be given by e to the power minus I by h bar v of delta over I delta j acting on W0j. But W0j is known already. We calculated earlier. So it is minus I by h bar v delta over I delta j acting on exponential I by 2 jx delta xy jy. And now you can just expand it in power series. Both of them are exponential. So expand the exponential, you get v greater than 0, greater than equal to 0, 1 over factorial v minus I over h bar v delta over I delta j to the power v acting on sum over p greater than or equal to 0, 1 over factorial p half ijx 1 over delta xy ijy to the power p. And so this is the result for w tilde j. So w tilde j is given by this expression, and let me call it equation w tilde. Now look at this final expression. You see v is given by, because of the discussion that we already had, it is a Taylor series expansion around phi equal to 0, v of phi. So, and it has phi cube, phi to the power 4, so powers of phi. If this is a power of phi, then this is a power of the derivative del j, and then v is also an integer power of that. So basically these are higher derivatives, each one here. So v equal to 0 is 1, and then all the other are higher derivatives of with respect to j. Okay, these various higher derivatives with certain combinations are applying on the summation over this on this exponential, and it has all powers of j appearing, even it has even powers of j appearing, because this is basically a power of the propagator with two j's, right? So so that is what it is. So that is what the nature of this expression is, and therefore you pick any value of v, a bunch of derivatives will act on this, and there is no j equal to 0. We are not setting j equal to 0 at the end of the calculation. It is, we are calculating w tilde j for non-zero value of j, and for any given value of v, a number certain derivatives of j will appear here, and those derivatives will act only on all those terms where sufficient number of j's are there. If it is number is too less, then the derivative combination will kill that. But from a threshold value to all higher values of p, the contributions will be there, and those are finally can be written as Feynman diagrams. So at the end of this calculation, you get an infinite number of terms, and those terms can be whatever derivatives are absorbed from whatever number of derivatives you have will absorb the same number of j's from here, but there will be other j's remaining which are not absorbed. So it's a power series in j. So that is the point here. So this expression is basically can be written as n greater than or equal to 0 t tilde n, where this t tilde n is a contribution at nth power of j. Okay, now Now I will describe certain general, talk about certain general observations about this result. There are two forms of W tilde that we just discussed. One is W tilde J is equal to W tilde 0 times Wj, and the other form just derived was T tilde 0 plus sum over n greater than or equal to 1 T tilde n. This last expression, I'm writing T tilde 0 separately, and all the other terms which are higher powers of J. Now, so diagrammatically, if you wanted to think about it, then we know from our previous analysis, the basic points about the previous analysis was that the generating functional can be written as graphs, sum of graphs drawn with lines, dots, and in the case of interacting theory, you will also have vertices. We did not have vertices earlier, but now you will have vertices. So generating functional can be written as Feynman diagrams which are drawn with lines or propagators, dots which are the sources, and vertices. Therefore, if you set if you set the J equal to 0, that is the case here. In this first expression, if you set J equal to this part is basically J equal to 0. The W of 0 is 1, so this is the J equal to 0 part. So this you obtain by setting J equal to 0. So whatever the diagrams that are appearing here, they do not have any dots. Okay. Similarly, the second expression, these are this n is greater than or equal to 1 for this bunch of terms, this set of terms, and those are the powers of J, but these has J to the power 0, and therefore there are no dots. So W tilde 0 and T tilde 0 are they contain graphs with no dots, and these are nothing but vacuum diagrams. We didn't see these diagrams before, but now we seem to be having them. For example, you just apply your imagination. We don't have to actually, because we have discussed such things in the word line argument, that 3 vertex will look like a phi cube will look like a 3 vertex. So you could, if you have a phi cube term in the Lagrangian, then there's a 3 vertex with which you can write a vacuum graph like this. There are no dots. I have used links, I mean propagators and vertices. So this is a 3 vertex. This is also a 3 vertex. You can also have another diagram, which is this. This is also a vacuum diagram. And if you have 4 vertex, you can have a diagram like this. This is a 4 vertex. Oh gosh. You can have a diagram like this. This is a 4 vertex here. So and so on. There can be, these are the examples of diagrams which are vacuum diagrams, and therefore these 2 forms imply that these 2 forms, if both of these 2 are correct, then it means that this W tilde 0 and T tilde 0 are same, and each T tilde n has a factor of T tilde 0, then only T tilde 0 or W tilde 0 can become an overall factor. So the two forms imply for n greater than or equal to 1, the T tilde of n is equal to T tilde of 0 times something else, which has dots Tn, yeah, and T tilde of 0 is same as W tilde 0. So basically, each T tilde n, and the point is that this each T tilde n is actually has a factorized form, which is T tilde 0 times Tn, where Tn does not have vacuum contribution. Yeah, then so that Wj will be 1 plus sum over n greater than or equal to 1 Tn. Right, where Tn's are diagrams with no vacuum pieces. Now, what is the upshot of this? What is the basic point here in this argument? And this is actually an easy way to see that there exist disconnected diagrams in W tilde j. That is because T tilde n has a structure like this, it means that this is a vacuum diagram multiplying another diagram which is not which has n number of dots, that is has j's. Therefore that is only possible if these two diagrams are disconnected. There is no there are two factors, so these are disconnected diagrams. And so that is the explicit it explicitly shows that graphs with vacuum and non-vacuum disconnected pieces will appear in vacuum, and non-vacuum means like with j sources. They will be disconnected pieces of that. One piece is vacuum and the other piece is non-vacuum diagram. They are appearing in W tilde j. However, more generally, disconnected pieces appear in both vacuum and non-vacuum sectors individually. So it is not that, so this just shows that vacuum and non-vacuum diagrams in a disconnected combination are appearing in W tilde j, but within this vacuum piece, dt tilde 0, you have all sorts of diagrams. If you have this diagram and if you have this diagram, there is no condition, there is no restriction that you cannot have a diagram which is this times this, which is a disconnected diagram, which is sitting inside this T tilde. So both T tilde 0 and Tn will have disconnected pieces. So more generally, so what one shows, so this shows that W tilde j contains disconnected diagrams with vacuum and non-vacuum factors. More generally, it has disconnected diagrams in both the individual sectors. Both within vacuum diagram contribution, which is W tilde 0, and the non-vacuum diagram, which is WJ, both of them will have inside them disconnected diagrams. This just shows this just shows us this just shows that the presence of disconnected diagrams, whatever I've just shown explicitly, is partially in the context of factors of vacuum and non-vacuum, but you can actually look at this, study this expression more carefully and convince yourself. We will do that in detail in a particular example, that both within the both within the vacuum and non-vacuum sector separately, there will be disconnected diagrams. So this contains disconnected vacuum, connected and disconnected vacuum diagrams. This will contain connected and disconnected diagrams with dots, with J's. Now our goal, so to summarize, therefore you could summarize it in this way, that W tilde J, which has the form W tilde 0 times Wj, then this one, what we learn, is the vacuum sector. And this is a non-vacuum sector. Both of them contain connected plus disconnected diagrams. Now, our next goal will be to understand the structure of connected and disconnected pieces. How there is a relation, because disconnected pieces are containing connected pieces, many of them. Is there any order in that relation between disconnected and connected pieces? So let's discuss that. So structure of connected and disconnected pieces. So recall that in the free theory, we had disconnected graphs. That disconnected graph is basically a product of set of connected pieces, and all possible such products appear in the generating functional. Let's go back and see in the free theory. In the free theory, we had only one connected piece, right? Only one topologically inequivalent connected piece. In an interacting theory, we might have many more connected units, but then the disconnected diagrams are just product of those connected diagrams, right? This is what we saw also in the word line discussion, that you just multiply them, and always, if you have two connected pieces, either same or different, you multiply them, another diagram is produced, and that's a disconnected diagram. So the point is that the claim is that in the in the generating functional, all sorts of those diagrams will appear. Okay, and one demonstration that we have seen that is true in the free theory, we have only one topologically inequivalent connected piece, and all combinations are appearing in the generating functional. So a disconnected piece, so in free theory, disconnected piece graph is the product of a set of connected pieces and all possible. So let me write it in free theory. This is observation 1 and observation 2. This is going to be observation 2. This is 1. In free theory, this is an observation: a disconnected graph is the product of a set of connected pieces. And then the observation 2 is that all possible such products appear in the generating functional. Moreover, so maybe I should just this is observation 1. Write it in more systematic way. Number 3 is that if you have in a disconnected graph, if you have a product of an identical connected piece, then that has a symmetry factor of 1 over factorial n, right? A disconnected graph with n identical, okay, so in identical connected piece, in identical connected piece in a disconnected diagram contributes 1 over factorial n as a symmetry factor. Sorry, as symmetry factor. Now, given the number of dots, given the number of dots which are the sources, say n, which is greater than or equal to 0, vacuum or non-vacuum, it's a well-defined problem. It's a well-defined problem to find all possible topologically inequivalent connected diagrams. All possible topologically inequivalent connected diagrams, which means that I have a set C in I, which is the which are the connected diagrams with n dots. Okay, if I tell you there's a propagator and there are certain number of vertices, 3 vertex, 4 vertex, 5 vertex, whatever it is, I give you the vertices, the primitive vertices, then find out, given a value of n, number of dots, what are the topologically inequivalent connected diagrams with n dots. This is a well-defined problem, and there is a set of such diagrams exists, and then I is varying over that set. So this is n is fixed because that is the number of dots, and I is changing. You can numerically count it 1, 2, 3, etc., or by some other means, but basically I runs over the set of elements belonging to that. I runs over the elements belonging to that set, the topologically inequivalent connected diagram. For example, if I have 3 vertex, then for n equal to 0, this is one connected diagram. This is one diagram. This is one of the CIs. This is another of the CIs. If n equal to, if you have a 4 vertex, then this one is one of the diagrams, one of the CIs for n equal to 0. Okay, so these are all connected. So that's how you have it's like a basis of connected diagrams. You have that basis. Okay, then let us consider W tilde 0, that is n equal to 0 for vacuum diagrams, will be given by any term. It has an infinite number of terms, but any term will be given by any term. For example, this term, this is in W tilde 0. This is one term. This term, so there are many infinite number of all these CIs are there, right? The full set basis. This is only one of them, right? But this term can be viewed as that CI corresponding to this. This is this term, this diagram to the power 1, and all the other CIs to the power 0. And therefore, any term, if you have these 2 factors of this, then that will mean that that term is this to the power 2 and all the other CIs to the power 0. So basically what I'm saying is that any term, any general term can be written as product of over I CI 0 to the power an integer or 0. If this is the basis, then a general term would look like, for each basis, each element to the power certain certain integer or 0, and then a product of. So if it is a disconnected, if it is a connected diagram, then that means ni is 1 for one I and 0 for all others. If it is a disconnected diagram, then ni is non-zero for 2 different i's, or ni can be 2 for one I, in which case it is a square of the same diagram, 2 pieces of the same diagram. But then that particular CI to the power ni will have a symmetry factor, because there are ni of CIs, and there can be a permutation among themselves without changing the contribution, and therefore you have a symmetry factor which is 1 over ni factorial. And then you have to sum over the whole set of ni's which are all greater than or equal to 0. This is the general form of W tilde 0. If you know the CI zeros, all the CI zeros, you can certainly straight away write down what W tilde 0 is, right? Then but this you can reprocess a little bit. Just take the product outside and then sum over ni greater than or equal to 0, ci0 to the power ni divided by n divided by ni factorial, and this is nothing but the exponential, right? So this is product over I exponential ci0, which is exponential sum over I ci0. Okay, I shall finish. I need some half a page. I will finish in this video and show the 2 pages at the end separately. So this is for the vacuum diagrams. Vacuum is W tilde 0. You have a structure, you arrive at a structure like this. And in terms of connected diagrams and all possible connected diagrams, finding them is a well-defined graph counting problem. Okay, so that has to be done case by case. Now let us move to the non-zero. So W tilde J. So W tilde J contains all possible diagrams with non-zero number of sources. So let us see what would be the general structure of WJ. So it's not W tilde J, WJ. WJ we should contain all possible diagrams with non-zero number of sources. So on the other hand, WJ contains all possible diagrams with non-zero number of sources. Right? So then WJ, what is the form that WJ should have? So this is for J, number of J equal to 0. Number of J equal to 0 means only the vacuum diagrams can contribute there. I mean, in each component I, only the vacuum diagrams can contribute. But if J is non-zero, then there are non-zero n CNs with non-zero n will appear, and that n is not fixed. It can be anything. You can have a diagram which has 3 dots, another diagram 5 dots. They are multiplied. So 3 dots is a connected diagram, another 5 dot connected diagram. You multiply, you get an 8 dot diagram, right? So J to the power 8. So that will appear in WJ, right? So you basically have to multiply the same thing, same object, same expression, but for different values of n, right? So you can have a product of, okay. So if if number of dots is 1, if n equal to 1, then you have if it has a factor, if at a particular time a term in WJ has a factor with n equal to 1, then right. So then that contribution will look like this. Then it can have a factor with n equal to 2, right? 2 dot diagram. So that will be C2 I2 to the power n I2 divided by n I2 factorial, and so on. And then you should sum over all these n i's, right? Just think about it. Think of any diagram with non-zero j, non-zero number of j's. You can see, you can check that you can write it in this fashion. I mean, by choosing some values of ni's, that will match with this. Okay. The reason you are having different n is that any term will have certain n, right? Any term has certain n. The diagrams that will contribute to that term, and the condition on those diagrams is that it can be disconnected diagrams. Each disconnected piece will have some value of n, such that all these n values sum up to give you the total n that we are looking at here, j to the power n, right? This contain this has j to the power 1, this has j to the power 2, j to the power 3, and so on, right? So by choosing these numbers, you can actually write any term, j to the power n term, both connected and disconnected. That's a claim. You can think about it and check that this expression makes sense. But then if you accept this, if you have agreed with this expression, then it is nothing but so all these individual summation can go through by the same logic, the previous slide, go through the products, and it will become the product of exponentials. So exponential sum over I1 C1 I1, then exponential sum over I2 C2 I2, and so on, which basically says that it is exponential sum over n greater than or equal to 1 sum over I Cni. Therefore, the final form looks like this. W tilde j is given by exponential sum over n greater than or equal to 0 sum over I Cni, and this you can call at the z tilde of j. So the W tilde j is equal to exponential z tilde of j, where z tilde of j has all sorts of connected diagrams only. Only C's appear there. Okay, and summation of sum of all the connected diagrams. But then n equal to 0 and n non-zero sectors can be separated. Then it becomes exponential z tilde 0 times exponential zj. This part is this part is basically this is nothing but sum over I C0 I. Here n equal to 0 term only, right? If you take only n equal to 0 term here, this is sum over I C0 I, and that is z tilde 0, and that exponentiated when that is exponentiated, you get W tilde 0, and this one is sum over n greater than or equal to 1 sum over I Cni. Okay, and that is your Wj. Okay, so Wj is exponential of Zj, and W tilde 0 is exponential of Z tilde 0. Z's are the sum of connected diagrams. Zj they contain all connected diagrams with sources, and Z tilde 0 contain all connected connected vacuum diagrams. There is no z at j equal. There are no, you know, you don't have z of j equal to 0. That is 0. Z of j equal to, because w of 0, j equal to 0 is 1. Z of j equal to 0 is 0. There is no. It does not contain any connected diagrams that does not have sources, right? And these are all here. And the reason we get these vacuum diagrams is basically the mismatch between is basically it's the appearance of the vacuum diagrams. These are all vacuum diagrams. The appearance of the vacuum diagrams is an artifact of the definition of W tilde. This one wj, the actual generating functional that we wanted to calculate, does not have any vacuum diagram, but we could not directly deal with the path integral, which is why we defined W tilde with free action downstairs in the denominator. So that's a mismatch. We should use the total action, and that changes the vacuum structure. And there is a mismatch. If you remember, that path integral of e to the power I by h bar s is basically the vacuum wave functional, the product of vacuum wave functional. So it is that we are taking wrong vacuum wave functional while defining W tilde, and that has to be balanced. And because of taking the wrong vacuum wave functional in the downstairs, we are developing certain vacuum diagrams, because these vacuum diagrams is a comparison, is a ratio between the perturbative between the interacting theory vacuum wave functional and the free theory vacuum wave functional. That it is a ratio of that. It is in this ratio. If you look at the perturbative, if you compare with the perturbative vacuum, then the not perturbative vacuum, in the free vacuum, you are comparing, you are trying to write the interacting theory vacuum in some sense in terms of the free theory vacuum, which is why you are seeing excitations in the vacuum. But if you had completely dealt with the interacting theory, then there is no vacuum diagram, because the vacuum state is defined by construction. Its overlap is 1. So that is why W0 is 1. That is the vacuum wave overlap. But this part is not. This part is arising because of that. Because of the way we defined it. But it's not a problem. This is a technical analysis that we did, and it is because of this we could actually write W tilde in terms of vacuum in terms of this Feynman diagrams, because we could extract out this potential part in the numerator, and that allowed us to actually write down the contributions in terms of the Feynman diagrams. But then we have to segregate different types of diagrams, and the understanding of the relation between disconnected and connected diagrams is crucial here in order to understand the structure, how it appears. So this is your final. The final statement is that Wj has all sorts of diagrams with sources when j is non-zero, and the way the disconnected diagrams appear is basically it's an exponential of connected diagrams. So exponential will develop powers, and because of those powers, we'll get disconnected pieces. So that's the message. So I'll now show the two slides separately.